So it seems, I think we all agree that dark matter has not yet been seen directly, so its existence is still a hypothesis that we have to test. But I hope I've shown you that there's observational evidence for an unseen source of gravity at times in the universe's history between 380,000 years, which is the microwave background, and today, which is 13.7 billion years, and on scales of 10 to the 7 solar masses, which is the smallest dwarf galaxies, to 10 to the 18 solar masses, which is the scale responsible for the microwave background fluctuations. And I will claim that a new weakly interacting massive particle is currently the only hypothesis which is demonstratively and quantitatively consistent with all these data.
Thank you very much. Are there some questions?
Yeah, just 2 points about your fundamental evidence for dark matter. In the coma cluster, whereas Wiki found it that you mentioned, you would agree that the discrepancy he found was something like, in your terms, a factor of 600. That was the missing mass discrepancy then. It's only a factor of what now, Simon? 4 or 5? And that depends on the Hubble constant. So you would agree that that fundamental bit of evidence has, in some sense, become much less, with the discovery of the X-ray gas?
No, I disagree, because the reason, I mean, the current discrepancy between the mass of the coma cluster and the baryon cluster is a factor of 5 or 6 that I agree with, but the reason is that we now see the baryonic component between the galaxies, the X-ray emitting gas. The discrepancy for the galaxies is still nearly a factor of 100. So he got a number which was too big because of the Hubble constant, as you say, but the discrepancy between the mass of the galaxies and the total mass of the cluster is still close to 2 orders of magnitude.
Another point, WMAP, you've got 30 sigma results. Sorry, you have 30 sigma results for parameters. If the errors are statistical accurate like you hope they are, but of course the more people that look at WMAP data, the more issues we find with that data. Some people find that the radio sources are more blurred in that data, that the telescope is blurred, and that would have and it turns out that would have a huge impact on the interpretation of WMAP results. Other people have for a long time talked about the anomalies at large scales. These two things may be connected.
This is not yet a debate. So if you have some urgent questions, please, because otherwise
there are no published data which show an error in the WMAP analysis.
That is not true.
Okay, so we can. Here's another question there.
Simon, a little bit more careful. Isn't it critical, for instance, already to accept that the clusters are realized? Because we know that they merge, they form substructures, and this means all the interpretations of the velocities and velocity dispersion, and also of the temperature and the density might be misleading.
The detailed simulations that I show you include all these effects, because we see the assembly of the clusters, so therefore we have the deviations from virial velocities, we have the internal motions of the gas. So it's true, these shift mass estimates by small amounts, but they don't shift the conclusion at all.
On the table where you showed the results of the WMAP analysis of anisotropes, the results for the parameters of the universe, there were 2 numbers there for the sum of the masses of the neutrinos.
Yes.
What is the difference between those 2?
This depends on whether they assumed a cosmological constant or they allowed a different equation of state for the dark energy. So if you take this one, then the upper limit on the neutrinos is a quarter of the mass of the baryons. If you take this one, it's just under half the mass of the baryons.
And these are entirely from WMAP data?
These are, no, here they're assuming, they've assumed, basically this is the local density, this is the length scale, so they have assumed a Hubble constant, which Tom would undoubtedly want to quibble with, but this assumes the locally valued, a particular locally estimated value of the expansion rate of the universe today. These are the values just with only the WMAP data. So actually for this particular, it makes a difference for this one, but not much for this one.
Okay, it seems there are no more questions, so thank you very much again. Okay, so you see the opposing view already in the title. And I guess we have now Pavel Kroupa, who will tell us about his point of view.
Okay. So, lambda CDM is ruled out, and I want to start with a historical perspective. 500 years ago, there was an excellent standard model, and that was the geocentric model by Aristoteles. One had to make the theory fit to the data by inventing epicycles on epicycles and moving the center of the universe, which was the Earth, away from the Earth to make it fit. It left an excellent description of the data. However, it was complex and a lot of people didn't actually like it so much. An alternative model existed by Aristarchus. That was the heliocentric model. It was not accepted because it was more complex and unsatisfying. There were two centers, and it does not fit the data. There were two centers because one had to have the sun as the center of the universe, around which the planets moved, and the Earth as well, around which the moon moved. So it was more conceived to be more complex and less satisfying. The decision came by technological advance when Galileo's solar system telescope data disproved the standard model. Galileo saw that Jupiter has moons. That means there were at least two centers in the solar system, the geocentric model, and that is the Earth and Jupiter. So the phases of Venus clearly show that Venus had to move around the Sun. And so a world beyond the standard model is seen for the first time through the telescope. However, at that time, there was absolutely no idea of what the deep physical meaning of that was, because Newton had not been around at that time yet, nor was Einstein. So the conclusions from this little historical escapade is that it is irrelevant today to debate whether the geocentric model fits any data. Also, beauty or even high precision of a model can misguide. The current worldview is that based on general relativity, that it is valid in the weak field limit. This can be tested by studying the dynamics and structure of galaxies, for example, in the local group and local volume, where we have the best available data here, and also that the matter is conserved, which means that it's produced during the Big Bang and is there since then. So this can be tested by studying the matter cycle. So this leads to a cosmological model in which structure is generated by dark matter into which baryons fall, fueling star formation activity of galaxies, as Simon has very beautifully demonstrated. And of course, this has to be valid in the local group and the local volume. So step one is we have a convincing, beautiful theory. It is the standard concordance cosmological model. Lambda CDM is equal to concordance cosmological model. Simon showed the excellent fits to many data which we have today. Step two is making the theory fit. Einstein-Newtonian gravity can only be made consistent with the data by adding inflation, dark matter, dark energy, dark force. That's a very new phenomenon which is now being discussed by Peebles and Musa, 2010 in Nature Review. So this is the standard concordance cosmological model. This has problems. Inflation is not understood really. The detailed particle physics mechanism is not fully understood. Dark energy has problems because the implied dark energy density is so small that it is unstable to quantum corrections. It is not seen by WMAP. At least there's an issue. Energy creation, which means universe expanding. You get more energy out of nothing. It's an energy creating model, and it may not be there at all, according to Wiltshire. Dark matter, despite much search hitherto unknown stuff, and whatever you do, you cannot falsify it, because there's always a particle just below the detection threshold of the newest billion-dollar experiment which you might be building. It is not falsifiable. Baryons, we've only seen a small fraction of what they should be. The rest of it does not seem to be accounted for. And dark force, well, totally unknown. Step three, an alternative exists. The primary arguments for Collloquium dark matter comes from flat rotation curves. So we've already had a discussion of this. We have here many rotation curves. The issue is here that as you go outwards from a galaxy, this is in kiloparsecs, from the center, you move up, the rotation curve becomes flat at some distance. For example, this is where the sun is at 8.5 kiloparsecs, and some of these rotation curves go out to 40 kiloparsecs. Now, Bosma, who was publishing this, concluded that perhaps a substantial fraction of the mass is not distributed in the disk at all. That means dark matter is probably in a spheroidal halo. This leads immediately to the problem that there exists an unexplained disk halo conspiracy, because the visible matter of a galaxy is declining exponentially outwards in radius, and the dark matter halo has to pick up just at in the right way to give these flat rotation curves in essentially every galaxy. And this is not explained. Flat rotation curves are in fact explained much better by non-Einsteinian turning gravity, for example by MOND or MOG, modified gravity and modified internal dynamics. So given an observed baryonic matter distribution, you observe a galaxy, measure its light, from that alone you can predict precisely the rotation curves, and you cannot predict the rotation curve using lambda CDM. Here's an example, this rotation curve. You see the wiggle. This is in MOND, because in MOND you only use the observed matter distribution to get the rotation curve. In lambda CDM, there's a mismatch here and there's a mismatch here, because you need the dark halo to give you the extra gravity. Plus, in MOND, dark matter significantly reduced in galaxy clusters. One does not need as much dark matter in galaxy clusters if one works in the framework of MOND. So there's a review here on that. Now, there are statements on large-scale structure formation. Simulations yield comparable results between MOND and the standard model for the large-scale structure. We show that it may be possible to reproduce observations of the cosmic microwave background and galaxy distributions with Bekenstein's theory of MONDs. And there's a perfect fit to the CMB peaks with the 11 electron volts sterile neutrino. So this is now the CMB power spectrum published by Angus, 2009, and you can see it's an excellent description of the data in a MOND framework. And here's a previous work by McGough, which was concentrating on the first two peaks, and it had no dark matter, cold dark matter.
Isn't that dark matter?
Which
11,
one?
11 EV sterile.
Yes, but it's hot. It's not cold dark matter.
It's still dark matter.
Yes, that's fine. Yeah, that's perfectly okay. So the numerical tools, anyway, so numerical tools are nowhere near ready, okay? Gary Angus writes this. Basically because the 2 or 3 people with the necessary expertise to develop the codes can't get jobs for love of money, which means we simply do not have the knowledge what a universe would look like in an alternative framework as we do in lambda CDM, because essentially nobody can do the work because there's no jobs for that. You can't build a cathedral with no people. So the concordance cosmological model does not uniquely account for the CMB nor large-scale structure. So there are 2 hypotheses, standard and the exotic gravity models, and in a perfect world we would of course be able to investigate both, but there are sociological issues. And here today young researchers are afraid and discouraged to try alternatives. This is unfortunately the case. This is why I'm mentioning this. There are some personal examples which I want to mention. For example, you have written that paper on DSPH satellites without dark matter. You are unhireable. It is not worth reading those papers on satellite galaxies, but everyone knows that MOND is crap. In Baltimore, 2010, this year, I heard it with my own ears. I would be scared, mostly because I'm still in search of a permanent post, of being labeled once and for all as a hardcore Mondian person, as if being labeled a hardcore LCDM person were acceptable. And I can't do any work on MOND. It would not be appreciated in the institute. So this is a no-go. And this is where what you do. That's the party line. That's where the resources are going. You do that to get a job. Now, step